The following is a selected video from masterthecontent.com, where you will find an extensive video library of lectures for a variety of standardized admission tests. We offer over 600 hours of detailed video lectures for a multitude of standardized tests. Use our interactive in-lecture table of contents to find specific topics of interest. Work through numerous in-lecture examples to help you internalize concepts. To learn more, visit masterthecontent.com. Your career, our passion.
Hi, I'm Jay. Welcome back to masterthecontent.com. Today we'll be covering another chemistry lecture, so let's get started by taking a look at our objectives. Today we'll be taking a look at the equilibrium in reversible chemical reactions, equilibrium equation, also known as the law of mass action, the equilibrium constant, and we'll be relating the equilibrium constants for concentrations and pressures, the heterogeneous equilibria, magnitude of equilibrium constant, and the reaction quotient. Okay, great. Let's get right into it. Okay, equilibrium in reversible chemical reactions. As we all know, chemical reactions can occur in the forward direction and they can occur in the reverse direction, and that's what's being indicated here by the double arrow. And when the rate of the forward direction equals the rate of the reverse reaction, then that's when it's said to have chemical equilibrium. So if we look here at our definition, chemical equilibrium occurs when the concentrations of reactants and products stay constant over time. Okay, wonderful. If we take a look at a reaction here now of dinitrogen tetroxide going to nitrogen dioxide, we see here initially we have reactant present and we don't have any product present. And with time, what actually ends up occurring is the rate of the forward reaction begins to slow and the rate of the reverse reaction begins to increase. And when these two reactions have the same rate, at that point it's said to have chemical equilibrium. Okay, great. Now let's continue this idea on the next slide. The equilibrium equation, law of mass action. So just a reiteration of what we just said, law of chemical equilibrium, law of mass action. At a certain temperature, the chemical system reaches a state where the ratio of reactant and product concentrations will have a constant value. And at that point, what's given is the equilibrium constant, as we will see. Okay, great. So if we take a look at this reaction here, when the forward reaction, so at equilibrium, when the forward reaction is equal to the reverse reaction. That's what's being demonstrated here. Now, we can take this equation and just rewrite it as such. Now, the rate constants for the forward and reverse reactions, the ratio of the rate constants for the forward and reverse reactions are equivalent to the equilibrium constant. Thus, because of that, we can rewrite this equation as such. Now, this equation right here, this is known as the equilibrium equation. And to the left here, we have the equilibrium constant, and then to the right, everything over here is called the equilibrium constant expression. Okay, great. When you're working with concentrations, we see here as a subscript C. When you're working with pressures, we see the subscript here as P. Okay, wonderful. Now let's move on to our next slide and we'll do an example. Perfect. Example, equilibrium constant expression. Complete the equilibrium constant expression for both equilibrium constants for the following reaction. Okay, great. Remember, equilibrium constant expression was everything to the right of the equal sign. So looking at a reaction here, we see ammonia is being synthesized, and for concentrations, recall for constant molar concentrations, we could just use square brackets. Okay, I forgot to point that out to you guys in the previous slide. So we just have ammonia here, and it's going to be raised to the what? The second power, right? Because the coefficients are telling us that. Now, in our reactant side, we have here nitrogen, right? And we also have here hydrogen, and it's going to be raised to the third power. Exactly. Wonderful. So now we also have to do one more here for pressures. When working with pressures, we just put a P here to demonstrate that. And then we have our ammonia, right? And it's raised to the second power. And our pressure here for, we also have nitrogen. And we also have hydrogen gas. And that's going to be raised to the, you got it, third power. Okay, great. That's all there is to that one. Now let's move on to our next slide and we'll do another example. Example, equilibrium constant. Okay,